Okay, so far in this course we have probably discussed about different kind of networking over the past few decades that has been evolved. So that is something we have already discussed. So now we will actually go inside the actual content. So we will start with the first thing that we have discussed, that is the circuit switch network. So we need to first understand how circuit switch network was designed, what are the aspect of it, how this was realized. So these are the things we will discuss. Once we do that, then probably we will progress to other part of networking. Okay. So in a circuit switch network, you will see that there are two things which are very important. One is multiplexing and the other one is switching. Okay. Of course, then synchronization is another part that we will be trying to discuss. So today probably in this class we will be trying to discuss about one of the specific switching technology, which is called space switch. So we will see what is this and how it is realized. Okay. So the concept in under circuit switch networking probably will be covering space and time switching. So today mostly we will be covering space switch and most of its design aspect. Then we will talk about synchronization, which is a very important aspect of circuit switch network. It has to be precisely synchronized. Why that is required, we will talk about that also later on. So that is something which we will be discussing next. And then finally, we will be discussing about multiplexing, various multiplexing schemes which are there. And of course, we cannot discuss all of them one after another. So in between there will be a mix of these things. So multiplexing will come inside space or time switching. So you will see those things, but we will try to keep the concept as much clearer as possible. Okay. So let us start talking about this space switching. So let us see what is actually space switching and how it is being realized. So two kind of space switching we will talk about. We will talk about one for local loop and another one for trunk. So we have already probably discussed. So let me again give some examples of that. So let us try to think about what is actually local loop. So we have said that maybe there might be some subscriber which are over here. So let us say some subscriber which are over here. Okay. So first what they do, they try to connect to the local subscriber loop, and from there we have already shown this diagram that it goes to some trunk where multiple such local subscriber loop connects to. Okay. And then it goes via multiple trunks in between, and then finally it gets connected to again some subscriber over here. Okay. Now whenever you are switching over here in this local loop, so what you require, one is that you have to go out, that is a different issue, but if you have to communicate within themselves, so it is a switching among themselves. Okay. So any combination might be there. So this is called the local loop, and when you are actually switching either going from here to this trunk, so this is the trunk portion. So either you go from local loop to trunk or trunk to trunk. This switching when you are doing, that is the trunk switching. Okay. So we will talk about the specific details of these things. So when you are in local loop, what you need is something like this. So you need a switch where let us say n number of subscribers are connected. So 1, 2, and then they need connectivity to means among themselves. That means if in the switch, if I see the output, let us say 1, 2, all those customers are at the output also they are connected, and what generally being done, so every user will have a transmitter and a receiver. So it is called transceiver. So every user will have this block. Now what happens, this transmitter I will connect to this things, suppose for user 1, and this will be taken out and connected to the receiver, and so on for every user. So for 2 also same thing will be happening. So his transceiver 2 will be connected, and so on. There will be n such users who will be there. Okay. So, now every user who wish to connect to other user, what you need to do is his transmitter and the other guy's receiver has to be connected and vice versa. So, this is something which you will have to do. So, that means basically if now user 1 wish to connect to user, let us say 2, then you need to give connectivity through this switch like this, user 1 to 2 and probably 2 to 1, something like this. Okay. If it is a means half duplex kind of thing. Okay. So, and if it is means completely duplex, then what will happen? One connectivity is okay, that carries the data from user 1 to 2 and vice versa. So, whatever it is, we need to give this spatial connectivity, and that is the switch we are talking about. So, that is the local loop switch. So, local loop switch will probably have as many number of input ports, that many number of output ports. This input port and output port are actually corresponding to every user. Okay. So, each pair of input and output port actually corresponds to one user. So, if we say user 1, it will have one input port and one output port. Of course, through the switch he will never be connected to himself. So, that is stupidity, that you do not go all the way to the switch and then connect to yourself, that will not be done, but to all other users you need to give connectivity. Okay. So, this is one kind of switch that we will be talking about, that is the local loop switch. So, this is the local loop switch. In trunk what happens? So, trunk is little bit different. If you see this example, so let us say there are multiple trunk links which are going out. Okay. Now, these users 1 to n. So, now let us think about the switch for the trunk. So, user 1 to n wish to connect to this trunk link. So, he wish to basically these users wants to go out. So, if he has to go out, he has to take one of these links. Okay. Any link is okay, because with any link he will be able to go somewhere out. So, basically in the output of the trunk there will be multiple trunk links. So, that might be different 1, 2 up to let us call m. Okay. Now, any user wish to get to this trunk, one of the links which are available right now, that can be given. So, basically it does not mean that user over here what was happening, if user 1 wish to communicate to user 2, only one possibility of linking is possible. So, 1 to 2 connectivity you will have to give, this connectivity you will have to give, because otherwise user 1 will not be able to talk to user 2. But over here whenever you are transferring something for let us say from user 1 to some remote location over here, it does not matter which trunk you take, because all of the trunk will be taking you possibly to the same destination. Therefore, you can take any of these available trunk. This is the flexibility the trunk switch will have. So, trunk switch is little bit different from the local loop switch. So, now trunk switch what I can do, any of the available link right now, okay, some of the links might be occupied. Suppose user 2 is already talking to means somewhere outside, so it has to be connected to trunk. So, he has been already given connectivity to user 1 probably, right. So, that is being already given. Now, what we need to do is now user 1 wish to make a connectivity. So, now all the available m minus 1 connectivity, any one of them he can take. So, I can connect him to to 2, 1 of course I cannot, because 1 is already taken. I can even connect him to 3 and so on up to m. So, anywhere I can give him connectivity. Now, once user 1 is connected, now next time if user 3 wish to get connectivity, now this connection is taken and probably I have connected user 1 to 2. So, that also is taken. Now, rest of the things I have to think about. So, this flexibility we have in trunk switching. So, these two kind of space switching as you have seen now will have to realize. Okay. How can we realize these things? So, let us first try to see this particular local loop switching. Okay. So, in local loop switching what we can do? We can do a switching matrix. So, how is that possible? I will just explain. So, let us say user 1, user 2 and there are n user, right. So, I connect this, everybody has a line and then I put a cross line. Okay. So, this is called crossbar switch. So, I put a cross switch or cross line for each user. Now, whichever connectivity and these things can be connected. Okay, so I can always give connectivity in these links. So, that is why it is called crossbar switch. So, it is a cross kind of switching matrix, and these are the switching elements actually. This is where I can give connectivity from one line to another line, and this is digitally controlled. We will see how these switches can be realized, how do I control these things. So, these are generally digitally controlled from outside. Okay. So, whatever digital input I give, accordingly they will be connected. Okay. So, now what I need to do, so whenever I wish to connect 1 to some, let us say 3, then I will enable these things. So, this will be with the digital control, I will enable this, immediately there will be a connectivity which will be constructed from 1 to 3. So, this is called a crossbar switch. Okay. So, in the crossbar switch, as you can now see, how many elements are required from n user if I wish to make a crossbar switch. So, clearly I can see n square number of elements are required. Okay. So, if there are n number of inputs or n number of users who are trying to connect to a local loop switch, then we need n square number of, in this kind of crossbar switch, we need n square number of switching elements. These switching elements are the costly part, because they need you will see a digital circuit and a control from outside. We will talk about that part, how those switching elements are realized in digital switching and how they are controlled. So, that is something we will be discussing later on. But for the time being, we are just giving this representative diagram as if from the output control we can connect any of the input to the output. Okay. So, as you can see, there are n square number of switching elements. Now, if we ask ourselves, and this is called the square arrangement. So, because you have this cross and bar, n square number of switching elements are there. So, it is very symmetric. So, that is why it is called square. So, square switching can be facilitated where n square number of switching elements are required. Suppose this is a full duplex. So, one connectivity I give 1 to let us say 3, then 1 can communicate to 3 as well as 3 can communicate to 1 via that same this one. Then can you see there is a redundancy over here. What is that redundancy? The first redundancy, let us try to understand. There is also a particular connectivity of 3 to 1 I can give connectivity. Okay. So, these switch and this switch, these two are redundant if I make it full duplex. So, if I make sure that if 1 is connected to 3, then 3 can also in the back direction means transmit to means either data or voice to 1. So, if this is happening, so only this switch is required. This switch actually is a redundant switch, it is giving me no purpose, any of this switch will do everything for me. Okay. So, as you can see, if I just explore little bit, I can see that means if I just from this square one, if I make it triangular, then all other half of the triangle is actually redundant. So, if I just make it something like this, one up to n, 1 up to n let us say. So, if I just bring, suppose first of all let us try to see the diagonal element 1 to 1, 2 to 2, is that required? 1 will not be talking to 1. So, basically these diagonal elements are not required, that is pretty much sure. In the off diagonal element I can see, as you can see, if I take this one, then this one is redundant. So, basically if I just take out the upper triangle probably, and if I take out the diagonal things, so if I only connect the lower triangle, that is good enough for me. So, if I just take this switching element, this and so on, like the entire these things. either I take the lower triangle or I take the upper triangle, one of them. So, if this is my whole matrix, so either I take this or this, any one of them will serve the purpose without the diagonal. Okay. What is the number of switching element now? I have done some reduction. So, what that will be? So, as you can see, it was n square, half of them I have taken. So, that must be n square by 2. Okay. So, that must be the case, okay. Half of them if we take, but if you see it is just not n square by 2, because I have also taken out the diagonal one. So, that means what will be the number? That should be n into n minus 1 divided by 2. Okay. So, if I take half, then out of diagonal half will be taken, that half n by 2 you have to take out. So, I get this, that is simply nothing but NC2, as many combination of connections you can have. This is something we already know, that if there are n number of users, how many connectivity you will have to give, that is actually NC2, because two of them will be talking to each other, as many possibilities are there, that is NC2, that many connectivity you will have to give. In the switch also we can see, if we have to give full connectivity to each and every users, this is the bare minimum that will be required. So, that means after reducing this switching number of switching elements, we have come to this magic figure of NC2, n into n minus 1 divided by 2. Later on we will talk about whether this is sufficient reduction, can we reduce further more, and what is the disadvantage of this one. Okay. But before that, let us also talk about the trunk switching. Okay. So, let us see the trunk switching part. Now, m trunks are there. Okay. What is the connectivity? Again I can construct a crossbar switch. At the output I will be taking, because m number of outputs are required. If I provide these connectivities, this is good enough. Now, wherever I wish to go, so 1, suppose initially everything output everything is free, I can give connectivity to 1 by enabling this one, okay, and so on. If now 2 comes, it needs a connectivity, I can give 2 to 2 connectivity, 3 comes, I can like this, any connectivity I can give, because over here I do not have a preference, any one of them is good for me. Okay. So, I do not have to put it either in 1 or 2 or m, which was the local loop switching requirement, but that is not there over here. So, over here if I try to see what is happening, if you just try to see, if any connectivity I give, I have so many redundant switching elements. Suppose 1 has to be given connectivity, I do it by 1 and all these other switching elements are redundant, they will further not be required. Okay. So, these are the redundant switching elements which are underutilized, that is one thing. So, that means lot of switching elements are not being properly utilized. Okay. But you can always say, if I just give 1 to 1 connectivity, then only one trunk is available for him. If he is not using that, and if anybody else is not really connected to, or there is a possibility of connecting him to any other users, then that will be underutilized again. So, basically whether it is a trade off between whether trunk should be underutilized or switching element should be underutilized, which one is more costlier? Of course, trunk is more costlier. So, that is why people have come up with this full blown switching elements, they call it rectangular matrix, or rectangular crossbar switch, right. It is rectangular because the input and output are no longer symmetric. Earlier it was called square because input output in local loop were symmetric. As many inputs are there, that many outputs were there. Okay. So, over here we call it rectangular, but in this rectangular there is also another extra things, that means the output is now no longer targeted, which output I have to put. Switch does not have to decide that, any one of those outputs are okay. So, that gives us an extra facility. You know what is that extra facility? Maybe some of the switching elements I can reduce. So, that reducing, let us try to give one example. So, let us say I have 8 number of users. Okay. Or let us take a simpler example, let us take 4 number of users. Okay. And let us say I have, okay, so for demonstration maybe let us take 8 only, 1, 2, 3, 4 up to let us say 8 number of users are there, and I have 4 trunk. Okay. So, for giving connectivity I need some amount of, means I should not fix it. So, basically I can take all these 8 into 4 connectivity, that I can do, but that is too much switching elements. Okay. So, instead of that I can reduce it little bit. What is the method of reducing? It is called like this, I can for 1 I can give 2 connectivity. So, he has 2 options. For 2 also I give 2 connectivity, he also have 2 options. For 3 I might give some other options. Okay. Similarly, for 4 I can give some other options. So, all kinds of possibility. So, suppose 5 and 6 I might give some other possibility. So, all kind of shared option I am trying to give over here. As you can see, each of these switching elements or each of this trunk are shared among multiple users. So, first trunk is not, earlier what was happening, first trunk was shared among all the users, every user has the possibility of connecting him. Over here I have made a subgroup by restricting the number of switching elements. So, what I have done, for 1 I have created among the user a subgroup of 4 user 1, 2, 3, 4, as you can see. For 2 I have created another subgroup. So, if 7 and 8 also I demonstrate. Let us say I do this. Okay. So, as you can now see that I have created a subgroup for 1 trunk 1, I have created a subgroup of 1, 2, 3, 4. So, these 4 users have the options of connecting to trunk 1. For 2, that subgroup is different. Okay. And each user also have multiple options, as you can see. User 1 does not have to always go through first trunk. He can either take first trunk, if first trunk is not available he can go to the second trunk, sorry, this fourth trunk. Okay. Similarly, for user 3 it is a different thing. So, with this I have reduced the number of trunk, as you can see I have now made it half. So, like this there is a possibility of reducing the number of connectivity or number of switching elements that you are putting, because you will later on see these switching elements are the costlier part. So, if a switch dimension has to be increased, so if I have to scale this switch, so n becomes very large or m becomes very large, which will be happening in actual switching. So, in that case the switching elements, that amount of switching elements that I will have to put, that will be dauntingly high, and I need to reduce that in my engineering design. So, these are the options of reducing things. So, this is called graded switching. So, this particular part, this was rectangular, that means full blown switching elements are all given. This is called graded. So, once I do this graded matrix, then definitely I have to do it very carefully, who should be in which group, who should give connectivity, means for whom I should give connectivity. So, all these things has to be carefully designed. Okay. So, these are the 2 options for, if I can say, for trunk switching. Okay. So, I can either take the full rectangular or I can take a graded rectangle. okay, where I will be means my target is always the same. I am just trying to reduce the number of switching elements over here also. When it was local loop also, I was almost trying to do the same thing. So, both the cases I am just trying to reduce the number of switching elements. So, now if I just ask myself that why I am reducing the switching element, one was very obvious reason that I want to reduce the cost. Is there any other benefit in reducing the switching elements? So, let us try to see what this switching element does. So, let us say I have this full blown switching, okay. I want to give a connectivity, let us say the first one I want to connect to the jth one, this is the jth one, I want to connect to jth one. Let us say all these switching elements are there. Now, what this switching element will be? There is some digital circuit, so they have some capacitive effect. You means whichever digital circuit you will take, they will have those stray capacitance, right. So, each of these element, if you see how one goes to j, so it has to go via this route. Now, when after doing the switching, when you go via this, it has to actually cross through all these elements, all these switching elements. More number of switching elements will be there, it has to cross through that, and all those switching elements will give capacitive loss. So, that means my signal will have a huge loss as I increase number of switching elements, because in the matrix if all switching elements are there, he has to pass through all these switching elements. So, all these capacitive loss will be incurred to him, and that will give the signal quality to be poor. If he has to go through multiple such switching elements, or the switch dimension is very big, which will be happening practically, so then you have a problem over here. So, as you can now see, we have two basically engineering aspects or engineering prospect that we have in mind, for which I need to reduce the switching elements or number of switching elements. One is if I have to scale, the cost of this switching element is going to be daunting. Second thing is there is this stray capacitor effect, which will give distortion and to my signal, to my actual voice signal, whatever we are transmitting, and it will also give extra loss to that signal. So, for these two reasons, will next onwards what we will be trying to do is there any further way of reducing the switching elements? So, that should be our major focus of the next 1 or 2 lectures. Okay. So, that is something we will be targeting towards reducing this number of switching elements. Either it is in trunk switch or it is in local loop. You will see that local loop and trunk switch will be little bit different, and accordingly while reducing them also there might be some differences. So, that something we will also try to appreciate in the next class. Okay. So, that should be our we will start this discussion in the next class. Thank you.